So we've looked at some interesting restoring forces so far in this series. We've looked at the traditional spring force, we've looked at the super spring, x to the fourth, and we've looked at the Lennard-Jones potential energy, one of my favorites. But all of those potential energies share a common feature that they're all power laws, right? So they can all be expressed in terms of x to the something, maybe plus x to the something else, but they're all power laws, right? We can also go beyond power laws and get a restoring force that can't be expressed in terms of a power law. For example, you might have your restoring force equal to a negative some number times sine of x, right? And x could be a position, but the classic example of this to think about is a pendulum, where you've got the pendulum here, you've got a ball hanging from a string, it swings back and forth under the influence of the force of gravity here and the tension in the string there, and x in that case could be this angle in here. We would usually call an angle theta, but we've been using x so far, so I'll be consistent with the previous videos. And so this thing ends up being oscillatory, right? Because your force is negative sine x, right? So it's going to be positive in one direction, negative in the other direction is always going to pull it back toward equilibrium. But this thing's not a power law, right? I definitely can't solve this, right? Because if I set this as m times d squared x dt squared equals negative a sine of x, right? So I make this my mass, actually this is going to be, this is going to be the moment of inertia for a pendulum. I could solve this for d squared x dt squared equals negative a over I times sine of x. So if you think of this in terms of calculus, I'm looking for a function that when I take the second derivative, it's equal to negative sine of the function. You can scratch your head for the rest of your life over what function satisfies that. We don't know. We don't have a name for it. We don't have a way to describe it. It's there. It's in the differential equation. Nature has no problem solving it, but there's nothing we can do to solve that. And so we have to use a computational technique to study this. We have to put this into a code. But we can do a little bit to try to understand it. Because since we're dealing with a sine here, there's this interesting thing called the small angle approximation. Two P's, approximation. As a physicist or engineer or scientist in general, the small angle approximation is one of your best friends. It says that if you've got a small angle, small meaning less than about maybe half a radian or so. It kind of depends on how well you're willing to take the approximation. In my classes, it's usually less than about a half or so. You can approximate this as just the variable inside. Because when you graph sine, right, here's theta, here's sine of theta. When you graph sine of theta, it goes like this. In that very first part here, it's very close to linear. It's very close to y equals x or y equals theta. So we could approximate this if we make a... So we could approximate this. We could make sure this is a small angle. In that case, your second derivative is approximately equal to negative number times this thing. And that should look familiar because that's just the spring equation. Right? This is negative kx. Or k over m times x. It's the exact same thing you had before. This is going to get you an x equals x naught cosine omega t, just like it did for the spring. Now, it's only true for small x, so once you get past big X, you're expecting this to be something else. But for small angles, we ought to be able to map it onto a cosine pretty well. Okay, so here we've got our negative sine of x restoring force, just like you have with a pendulum. One of the things I want to adjust here is instead of graphing x, I want to graph x modulo 2 pi. Since we're interested in a thing that's oscillating around kind of in a circle, we don't want this to grow beyond 2 pi unnecessarily, because then it looks like it's increasing. Well, no, it's really just continue to go around a circle. So I'm using the modulus operator to just say, take this number, divide by 2 pi, and give me the remainder. And then we'll do the same thing here on our phase space plot, just so that way we know when it's actually repeating itself around. Okay, so I've turned off damping, I've turned off driving. Let's see what happens with this pendulum restoring force. Okay, so we're starting off with a pretty small amplitude, as you do. It looks like we're getting a pretty good approximation to a cosine, right? So for the small angle approximation, this thing should give us a cosine graph, just like simple harmonic motion. And there you go. We get our regular cosine graph. We've got a period of about, I'm guessing that's right on 2 pi right there. How long did I make the time run for on this? T less than 100. All right, let's just make this t less than 20, just so I can get a trace on that. And down in the phase space plot, if this thing's behaving like a cosine, then this should be coming around like an ellipse, like we had previously. And sure enough, there we go. It's going around an ellipse, just like it did for simple harmonic oscillator. So for a pendulum, going from a small angle allows you to use the results from simple harmonic oscillator pretty well, pretty accurately. Okay, so let's check the frequency, the period here. So I got a period of about 6.28, right on 2 pi. So this is giving me a period of 2 pi for an amplitude of 0.1. So let's give it the old amplitude test. Let's make this bigger, but let's still make it a small angle for the small angle approximation. And we'll press Control 2 to run. So we'll see what happens. Our amplitude is doubled automatically because we're starting at higher. But again, we should still be within the small angle approximation range. So we want to see if our frequency is affected. And we are cresting the rise just after 6. So it looks like no. It looks like we have not broken the small angle approximation just yet. We might have moved out a little bit. It's kind of hard to tell. Yeah, no, we're still at about 6.28. Yeah, we're still right on 2 pi. All right, so for an amplitude of 0.2, we've got a period of still 2 pi-ish. Okay, let's increase this. Let's try to get beyond the small angle. Let's try an x of 1. Let me just compare that. How bad is sine of 1 radian compared with 1? All right, sine of 1 radian is 0.84. That should be notably different. So let's see what happens to our period now. We also, of course, want to take a look at what happens to the shape of the graph, because as this thing moves away from the small angle approximation, we would expect it to stop looking like a cosine exactly. Ooh, we've definitely moved. That's definitely past the 6.5 mark there. We can also take a look at our phase space plot. It's kind of hard to tell if it's departing too much from an ellipse. It looks pretty elliptical, I think. It looks pretty symmetric. All right, so let's take a look. Oh, yeah, we were at 6.7. So at an amplitude of 1, we're at 6.7. All right, let's move beyond there. Let's go ahead and bump this up to 2. Remember, there's no point in going past 6.28. So let's go all the way up to 3. Let's go up to almost pi. So this would be releasing the pendulum from almost a horizontal position. So it's rotating about 180 degrees here. All right, we are definitely not hitting a period of 6.28. And you look at the shape, this is definitely not a cosine, right? This peak up here is way too broad to be a cosine, right? You've seen plenty of cosines on your graphing calculators by now. You know, or on Desmos or whatever it is people use today, you know that that's not a cosine, right? This is much too U-shaped to be a cosine, right? Cosine needs to be a nice, gentle cross between a U and a V. This is definitely U-shaped, and we're getting a period right at about 8. So while that finishes up, let's record that here. I've got an amplitude of 3 and a period of 8. There we go. Yeah, so this is definitely not a cosine, right? It's definitely not behaving like a simple harmonic oscillator anymore. Let's take a look at the phase space plot. Now, that's quite different. Stare into the eye of Sauron here. Wow. Yeah, so what would be interesting would be to, keep changing those amplitudes and watch how the phase space plot changes. So you do this for a few seconds and you get a different phase space plot. Actually, let's do that. So for example, what I can do is just have this thing repeat itself over and over again for several different values of x. So let's try this here. So let's go with for x in, and then let's just get some different values of it. So let's get a 0.1, let's get a 0.5, let's get a 1, a 2, a 3. Well, we can go in between there too. Let's have a 1.5 and a 2.5. So what I can do is loop over all these different values of x as my starting value. Let's see, I don't need to create a new graph each time. I just want them to appear in the same window. So I can get rid of that here. There we go. So, but I do want to reset the curve each time. And then I do want to reset the phase space curve each time. Let's see, is there a way I can change the color on this? Yeah, I suppose I can. Let's do a red value equal to 100 and a blue value equal to 0. And what we'll do is in each go of the loop, we'll just say red value needs to decrease by, how many of these we got? We got 1, 2, 3, 4, 5, 6, 7. I would pick 7, wouldn't I? What's 100 divided by 7? It's about 14. Okay, so we'll go with that decrease by 14 each time. Go with our, go with our blue value increases by 14 each time. Wait a minute, I'm missing a number there. There we go. It's like red and blue do not have the same number of letters. And then what I can do, when I go to the color, I can say vector red value, comma 0, comma blue value, because whenever I give a vector to the color value, I'm saying here's the amount of red I want, here's the amount of green I want, here's the amount of blue I want. And then we'll do the same thing over here. Copy, paste. There we go. And I suppose I could, I don't think we need to give a label. It'll start to get, this should be pretty straightforward to watch this go. Cool. So we're going to let this run for a little bit, and I'll put this part in fast motion for you. All right, as always, I've forgotten how color scales in VPython, so I'll fix that before posting the code for you to use. But you can tell which one these are based on the amplitude in the x direction, right? So this is the half, this is 0.1, this is a half, this is 1, 1.5, 2, 2.5, 3. And you can really see the phase space plot gets bigger, right? Because we're pumping more energy in, but it starts to get more squished, and it really, right around here between 2.5, and 3, it really starts to get distorted from an ellipse. So it's really around the 2 to 3 mark that's really starting to get distorted. I think we can also tell that over here, you can start to tell where it's definitely not looking like a normal cosine graph, which is pretty cool. All right, let me fix that here. That do it. All right, I think that fixes that. Okay. Okay, let's comment that part out for right now, because I do want to look at one more thing about what happens when we add in the damping and driving forces. So let's put in a damping coefficient of 0.01 and a driving amplitude of 5 and driving frequency of 1. I did comment out my animation loop here, so let me just grab, let me go ahead and grab all of this stuff right here. We'll copy that and we'll paste that up here. There we go. Now I should be able to keep both of those in use here. All right, so, and let's increase the time for this as well. I want to see what happens to this system when we add in damping force and driving force. Red value, oops. Sorry, let's put these back to color.red and color.red here. There we go. Control 2. X. Oh yeah, and I need to initialize my X. There we go. Control 2. All right, so I don't start out with what I got before, right? So this is dramatically different than what we had the last time. Because remember, kind of like we had before, we've got the sort of oscillation within an oscillation, because we have the sort of natural frequency, that's the sort of broader oscillation here, and then we have the driving frequency laid over on top of that. If I come down here, the interesting part is what happens to my phase space plot. This is dramatically different, right? This is something we did not get in any of the stuff we had last time, right? We always got this nice loop. Here the thing is curving back around on itself. This is where we start to get into chaotic behavior, because this is where we start to get into stuff where the motion never repeats itself, where it eventually covers the entire region. It covers every point within some region. See, here it's even trying to follow itself, but it doesn't quite get back to there. I can also make a slight change to the initial conditions, and it will change the way this thing behaves. So like, for example, let's see what happens if we change our X from 0 up to 1/2. I'll press Control 2. And you notice here, I'm getting a pretty different shape compared to what I had before. It's got a lot of the same features in terms of looping around on itself, but if you overlay those on top of each other, they're going to be different shapes. And of course, we can try that out, right? Yeah, let's try that out. So let's see what happens now. Let's go back over here and let's comment out this part. And let's bring our looper back in here, because we are looping over the X values here, the starting X values. And how long will I need this to run? I should be able to just have this run for 20 seconds to get an idea of what's changing. Yeah, that ought to be fine. So we'll leave this at t less than 20, and now we're just going to loop over all these different X values, and I'll put this in fast motion for you.
All right, so this part is interesting. We're getting to these higher amplitude systems here. You notice how it's darting back along here? Let's see if we can see that up here. Yeah, see how it's getting up past 2 pi. Because we're using modulo 2 pi, it's jumping back down to 0. So what's really happening here is that it's continued to spin around and around and around and around. But because we are looking at an angle, we're doing the modulus. And so this little break here you're seeing is the modulus. So in principle, this thing could be continuing on and on here. We're just seeing what it looks like kind of in this region. Really interesting here, it starts to kind of turn around on itself. So this is where it would be oscillating back the other way. How many curves we got so far? 1, 2, 3, 4, 5, 6. Okay, here's our last curve on this wonderful chaotic animation. You can already tell we're not getting the same pattern on any of these. We're getting the same general idea, but they are drastically changing based on the initial position. So yeah, you can definitely tell here that the initial conditions have a pretty dramatic effect on how these things behave, right? So we've got different period, we've got, I mean, obviously we're going to have different amplitude, but we got different periods, we got really kind of a different shape to the phase space plot, right? You can imagine these things continue to, you know, swirl around like this. They get kind of the same general idea with how they loop back around on themselves, but these last couple, they are behaving dramatically differently. And so we say that something is going chaotic. This is what we have in mind.